Okay, good morning, everyone. All right, so this is our final lecture, okay, for our module this semester. All right, so for this today's lecture, we have a few things. Firstly, I'll finish up the last chapter on the virtual memory, all right, and DMA, and then we will also go through the tutorial 8 in today's lecture itself. Okay, so the lecture, I think about 1 hour or so should be done. Then we'll go for a break. We'll come back to the tutorial. Okay, and after that, I think tutorial questions are fairly easy. All right, so I think for maybe about 20-25 minutes we should be done, and then we will have some discussion on some admin matters regarding the project as well as the final exam. Okay, so let me get started here. Okay, can everybody see my screen here? Okay, thank you. Okay, so yeah, before we start, firstly, I'd like to apologize for last Friday's the lab aircon issue. Okay, I think even Uncle Jalil was not aware that the aircon would be turned off. All right, so it was like a last minute thing, and we tried to get it up, but it still had some issues. Okay, but I think he said you all managed with the doors and windows opening up and everything, so I hope it was fine. Okay. Yeah, hopefully by next batch the new makers lab will be up and running. Okay, maybe we can run the module there. Okay. Okay, so let's get started with this topic, virtual memory and DMA. Okay, so the whole idea is to understand, all right, the concept of memory allocation, all right, in terms of the OS, all right, and how so this virtual memory concept helps us to make use of lesser memory, all right, while the OS has a perception that it has more memory. All right, so that's the whole idea of this virtual memory space. Okay, so just some slides on the history. Okay, so if you of course go and Google or you look at YouTube and so on, you will probably see a lot of interesting videos on how memory technology has evolved over the years. All right, so these are just some examples, okay, of it starting off. So in the past, it used to have these memory tubes, okay, and then we went on to using magnetic core, all right, and then of course over time technology improves, and we are now be able to sort of compress more memory into very little space. All right, so again, this is quite an old technology, DR2. Okay, now we are already DR4. All right, okay, and this is just another sort of memory chip that you probably would see if you were to open up your computer right now. Okay, so in terms of the capacity, okay, it has been growing, okay, for many years, okay, but I think right now this is also not updated yet. Okay, if you look at it right now, it is sort of hitting a sort of a plateau, right, where it's sort of tapering off, okay, because there's a limit to how much we can squeeze in, all right, into that little space. Okay, so it is sort of tapering off, but I think it's already a very high level. Okay, and of course, when they come up with some new technology, new way of doing things, then again you will have another explosive growth. Okay, I mean, if we take for example SSD. Okay, SSD right now, of course, every computer has it. Okay, all your portable hard drives are made done using SSD technology. All right, but this SSD technology was a research topic or research interest about 20-25 years back. Okay, so it was still very much in the research area. You know, there were a lot of students doing projects in that field. Okay, but then fast forward 20 years now, everybody is having it. Okay, so similarly, okay, things that are being researched now, things that are being developed in the labs right now, it will take time, okay, before it starts to reach the stage where it can be mass produced and everybody has it. Okay, so I think the growth will always be there. It's just that new technology will take over. Okay, so in terms of bandwidth, okay, so this is of course important as well. Okay, how fast? Okay, so you want memory, you want a lot of memory in a small amount of space, but at the same time you want it to be fast, correct? You want memory access to be as fast as possible. So the bandwidth is also growing, okay, every year, okay, again, because of, again, when you say technology, it could also be the manufacturing process. Okay, the way you manufacture, you can have a better process, so that helps to maybe have some performance improvement of the product as well. Okay, so if you look at the growth, okay, what we have been generally seeing is that the capacity is always growing at a faster rate compared to the bandwidth. Okay, so what that sort of leaves us is with this sort of performance gap, okay, where I'm able to have my CPU performing at a much higher rate, all right, whereas my memory performance is not keeping up. Okay, so your CPU is very fast, correct, in terms of the processing and how it executes instructions, but the rate at which the memory access happens is still a lot slower compared to the processor. Okay, so that is what we call here the memory wall, right, where the RAM access latency, okay, is many times more than the speed at which your processor is running at. Right? So this becomes an issue. Right? That means your processor can execute very fast, but then it's just being slowed down because of the memory interface that it is dealing with. All right, so in terms of memory technologies, okay, in terms of speed, we say we have SRAM. All right, so those are done using transistors. All right, so we're not going to go into the details of how we build each memory cell. Okay, but basically transistors form the basis of SRAM cells. Okay, of course the problem with SRAM cells is it is low density. That means you need more sort of a bigger footprint to hold the memory space. All right, but it's very, very fast. Okay, then of course, since we wanted more space, the DRAM became very popular. Okay, because it only consists of one transistor and one capacitor. Okay, compared to one, for example, this SRAM cell which has 4 transistors or 6 transistors here. Okay, so in terms of the actual design, DRAM was simpler, so you could have a higher density. Okay, but then it also came with slower access. All right, so of course we have to have some trade-off, and then you also have the other technologies. Okay, so in the past we used to have the sort of disk-based hard disk. Okay, now you have SSD. All right, but the whole idea is you have some other memory to store large amounts of data. All right, and those kind of memory access is typically slower than what you have for your SRAM or DRAM. Okay, so if you sort of put everything together, you can sort of see that at the fastest end you have your registers. So these are the ones that are built directly into your processor. So if you take ARM, for example, you have your R0, R1, and so on. So you have all those internal registers. Okay, those are of course extremely fast because they are built into the processor itself. Okay, but they are of course very limited. Okay, so it all depends on whichever architecture you choose, how many internal registers there are to hold information. Okay, so of course when you have more registers, it means that I can hold more data while I'm performing the computation, so I don't need to access memory so much. All right, so that is the advantage you have. But again, since it is built into the processor itself, it's considered very expensive. Okay, because your processor itself is squeezed to the max. Right, you try to put in all your peripherals, your subsystems, everything inside that one single chip. Okay, so you can't just dump 500 registers inside there. Okay, then the chip will become super big. Okay, so you are limited by the size that you have. Okay, and of course, since in general most processors you sort of target it to be general purpose, you do not want to make your processor so big and so expensive just because you want to have more registers. Okay, so you have to have some sort of trade-off between a reasonable number of registers, okay, for programming, okay, while you maintain the size and the cost. Okay, now besides or outside of the processor space, because this is the processor space, you have your memory. Okay, in this case it is your SRAM or DRAM. All right, so this is where you can keep sort of a copy of your information that you want to access regularly. So you can have SRAM and DRAM or a mix of both, okay, depending on how you design the system. And the main bulk of the information is of course inside your hard disk space. Okay, where you store all the bulk of the information, and that is of course the slowest. the slowest to access. Okay, so of course, ideally we would like this, correct? We want a lot of memory that can be accessed very fast and at the same time very cheap. Okay, so this is currently not available. It might be available, all right, maybe sometime in the future, all right, so we do not know. Okay, so if such a thing becomes available, then of course it leads to a lot more or opens up a lot more doorways to what you can achieve, correct, with your platform. Okay, but currently that is not available. So what we want is we want to sort of have the best of both worlds, right? And that can be achieved, okay, using what we call a hierarchy of memory systems. All right, where small and fast memory is near the CPU, okay, but the larger ones are further away. Okay, so that sort of brings us to this memory hierarchy. Okay, so at the fastest, okay, you have your internal registers. Then you have some RAM, SRAM, and DRAM. All right, and then finally you have your disk. So as the base, you can see that the size is of course the biggest for your hard disk, and then it sort of gets smaller and smaller as you go towards the processor. Now, in order for me to sort of use this hierarchy efficiently, okay, I can sort of take advantage of this concept of principle of locality. Okay, and this principle of locality basically says that a program accesses only a small portion of the memory address within a small time interval. Okay, so what do you mean by this? Okay, so this locality has two aspects to it. One is the temporal, the other is spatial. Okay, so temporal locality means if I access a particular variable, chances are I will access it again somewhere in the near future. All right, so if you look back at your code, that is usually what you see as well. All right, if you have a variable x and you load a value into x, you will probably use that variable for a few lines of code, okay, while you're doing some calculations before you move on to something else. All right, so the temporal locality is sort of generally there, okay, for most of the memory or the variables that we use. Similarly, there's also the concept of spatial locality. All right, why? Because in many parts of our program, we may use arrays, correct, to store a lot of data. So in that sense, when you access one variable, okay, so if I access one variable, chances are I might access variables that are also nearby it as well. Okay, so of course this is not always the case, but for a good chunk of a time slice, you can actually see that this sort of holds true. Okay, so what we are interested in is this what we call a working set. Okay, that means I take a particular sort of time slice of my entire system, and if I look at that time slice, you can see that this concept of locality holds true. Okay, so of course it's not throughout the entire program, but for that period of time, you may access that particular variable again and again. You may access nearby variables again and again. Okay, so that holds true for both programs. Okay, because we may have loops and as well as data because of arrays. Okay, and similarly in the stack usage as well. Okay, when we are using variables and we want to save and push and pop from the stack. Okay, so this working set concept, all right, gives us this idea that there is always this group of information that is regularly accessed for a particular time period, okay, which we call the working set. All right, so what we want to do is we want to exploit this. All right, and there are two ways to do this. Okay, one is of course the concept of it making visible to the programmer. All right, so certain things may be visible to the programmer in terms of actual coding. All right, so if you were to go into the assembly level, okay, you can manually sort of assign variables to registers and maximize the use of it. All right, but again, this may generally be handled well, okay, if your compiler is able to do it. All right, then of course the other thing is the concept that is transparent to the programmer. Okay, so this transparency is basically the OS, okay, sort of handles it, okay, where the OS looks at it as a single address space, okay, and the memory allocation is done okay, depending on how the usage is being sort of utilized. All right, so we will look at that. Okay, so there are two things, right, to this. One is we want to make slow memory, okay, appear faster. Okay, so what is the slow memory? The slow memory is the DRAM. Okay, so we know DRAM is good because we have we can pack a lot of sort of DRAM cells into a small footprint. All right, so the density is there. Okay, but it's not as fast. All right, but SRAM is very fast, but it's expensive. Okay, in terms of the footprint. So how can we sort of mix both of them together? We can have more DRAM and just a small amount of SRAM that works as a cache. So the whole idea of a cache is you keep a small amount of memory, okay, within the processor space, all right, and as and when you fetch from the DRAM, you actually keep a copy in the SRAM. Okay, so subsequent access, okay, within that working set, okay, will be mostly confined to the SRAM. Okay, if it doesn't get it in the SRAM, then it goes out to the DRAM and so on. Okay, so that cache concept was introduced, okay, in the 1960s, and that is where you can see a lot of improvement, because now you are able to maximize the speed, okay, of the SRAM cache, okay, without being too delayed by storing everything in the DRAM. Okay, so this is hardware managed. Okay, that means if your processor already has a cache built in, okay, it will automatically manage this. All right, so you do not need to think about what goes into the cache, what goes in the DRAM, and so on. Okay, automatically the hardware handles it for you. Now, the other thing that we are going to be focusing on is this concept of virtual memory. Yeah, in this virtual memory, what you want to do is you want to have an idea of how to make a small memory appear bigger than it is. Okay, and that is actually OS managed. Okay, so that is what we are going to be covering today. But the idea behind it is actually similar. So cache and virtual memory have a same concept. Only thing is, in the cache, you are talking about SRAM to DRAM, whereas in the virtual memory is between the DRAM and the hard disk. All right, so that is the sort of differentiation. Okay, but the concept is actually the same. So once you know one, you can easily apply it to the other. All right, so again, this is just another slide of the hierarchy. So I'll not go through again. Okay, so this is an example of how a system might be designed. All right, where we have your CPU with its internal registers. Okay, and most processors now, they have level 1 or level 2 cache. All right, where they split up the cache into I and D. So one for instruction, one for data. Okay, and then you have another level 2 unified cache. Okay, which takes sort of a memory copy from the actual main memory, which is your DRAM. All right, and then finally you have your hard disk space over here. Okay, so this miss penalty, okay, we'll come to that in a while. So this miss is basically the case where you try to get it from the cache, okay, but you are not able to, correct, because it's not in the cache. So when it's not in the cache, then you need to go one level higher, correct, either the main memory. If it's not in the main memory, you need to go one level higher to the hard disk and so on. Okay, so there's always this miss penalty that you will incur, okay, when the information you want is not where you think it is. Okay, so that sort of provides or gives some performance degradation. Okay, but again, overall, because of the principle of locality, your chances of getting a hit in most cases is higher. All right, of course, unless you intentionally or the code is written in a way that is not able to optimize the cache or so on. Okay, then you have another issue. Okay. Okay, so the whole idea of virtual memory, all right, is that you want to make a small amount of memory, okay, available to the CPU as if it has a lot of memory. All right, so that is the idea. Okay, so just to recap, so when we talk about process, we already know that a process is just an instance of a running program. Okay, in our case, like I said, we can sort of interchange the terms process with task, okay, or thread. Okay, so as long as the concept is there, then we sort of interchangeably use them. All right, and we know that when we create a new task or a new process, we take it that each process has exclusive use of the CPU. All right, and it has its own memory set and everything. And while it is running, it's able to make use of the memory and the CPU that is allocated to it. Okay, then of course there's the concept of context switching, okay, between the different tasks, okay, as and when the scheduler decides. Okay, this allocation of how or what goes into which portion of the memory space we saw last week, okay, of the text, the data, the BSS, the heap, and the stack. Okay, so we already discussed this last week. So in terms of virtual memory, okay, what do we have? All right, so when you say virtual memory, all right, the idea that we're trying to solve is how do we address all the space that we have, okay, to map to the code that we are trying to run on it. All right, so we want to create some form of a mapping, okay, between the code that we have written, okay, with all the data, the variables, everything, to the actual physical memory that we have in the system. Okay, so for example, if I say I have a system with 64-bit addresses, okay, so with 64-bit addressing, I have a total access of 16 exabytes, which is a lot of space. All right, but my actual main memory can be very little. Okay, maybe only a few gigabytes of main memory. All right, and at the same time, I have so many processes that are running, or so many tasks that are running. So how do I fit everything inside this small memory space that I have? Okay, so you have to understand that also each process, okay, that you create has its own set of stack, heap, text segment, data segment, BSS, and everything. All right, so if I have n processors, I have n multiplied by the amount of space that each process needs. Correct. So how do I allocate all of this into a physical memory that is limited in size? Okay, so that is the key thing we are trying to solve with this virtual memory. Then there are also other challenges, right? If I have a memory that is shared, okay, a block that is shared, okay, between two processors, how do I protect this memory space? Okay, and at the same time, if both of them are reading it, how do I allow this shared access to a common memory space as well between two processors? Okay, so again, these are some of the issues we want to highlight. Okay, so again, these are the problems we want to solve, okay, using virtual memory. So the first thing is we bring about the concept of indirection. Okay, so what is indirection is basically the concept of a pointer. Okay, so with indirection, what we are saying is instead of saying that I map my a name to a direct memory space, I map it to some other block that can decide which memory space it is going to use later on. So at one time, I may use this memory space, another time I may use another memory space. Okay, but ultimately that layer is transparent to me because I still reference the same block here. Okay, but what that block points to can change. All right, so that is the idea of indirection. So this makes it easier, okay, because you now just look at the reference or the pointer, and the pointer may point to some other actual physical memory, okay, depending on what was happening at the time. All right, so that is the whole idea of how this virtual memory is going to work. Okay, so you have multiple processors, process 1 all the way to process n, and each of it requires a certain amount of space. All right, but all of those processes cannot fit into the physical memory at the same time because the physical memory is limited. Okay, so we need to do some form of a mapping so that I'm able to map my virtual addresses to the physical memory. So that is the key thing here. Okay, so how does this mapping go about? So firstly, I need to have a virtual address space and a physical address space. All right, so the virtual address space can be given as say n bits, so you have 2 to the power n addresses, and physical is 2 to the power m. All right, so n is always greater than m, okay, because your virtual space is very big. Okay, and then you are trying to map it to a physical space. Okay, so this is your n and this is your m. Okay, so you have a lot of virtual memory space and you try to map it, okay, to a physical address space. Okay, so when you do this, okay, so traditionally, okay, in a simple, let's say, embedded microcontroller, okay, you are able to directly access the memory as it is. All right, so when the CPU puts out an address, okay, that I want to access, for example, 0x A0000000, I directly am able to point to that particular memory location and access the data. Okay, so that is of course for simple systems where you don't need this virtual memory. So a simple embedded microcontroller will work with direct physical addressing. Okay, but with virtual addresses, what you need to do is you need to do a translation. Okay, so that translation is done using what we call a MMU. Okay, this is a memory management unit. Okay, so what this memory management unit does is it does a translation of the virtual address to the actual physical address. Okay, so the CPU takes note of the virtual address, all right, that is going to access when it's dealing with any particular process. But the actual physical address it maps to can change, all right, and that sort of information is maintained within the MMU. Okay, so what is the information you need? So to do this mapping, okay, what you have is what you call this virtual memory pages. Okay, so virtual memory, okay, is basically 2 to the power n contiguous bytes stored on the disk. Okay, and you partition that into pages. Okay, where you have a certain page size. Okay, and what you do is you use the actual memory, the DRAM, as a cache. Okay, so this is what I mentioned just now. The idea of caching is actually the same idea of virtual memory. Okay, only thing is that is one level higher between the actual disk and the DRAM. All right, so the whole idea is the same. Okay, you have a lot of pages in the virtual memory. You only have a limited number of pages in the physical memory, and you want to do a mapping. Okay, so when you do a mapping, as you can see, what is happening here is, for example, here this page over here, VP1, is considered cached. That means I have a copy of this page inside my physical memory as page 1. Okay, physical page 1. So with that, it means that when my access to this memory region is required, okay, I can straight away access it through the physical memory, which is the DRAM, without having to go to the hard disk. So my access is fast. Okay, now of course there will come a point of time where you may miss it. Okay, it's not there, then what do you do? Okay, so we will come to that in a while. Okay, but the idea, as you can see, is I have a lot of pages on the virtual memory side. Okay, and as and when I need, I copy those pages over to the physical memory to use it. Okay, so that is the idea. So in terms of a virtual memory page, you can say it is unallocated. Okay, that means I am not using this process. This page is not being used by the process. Okay, so it is not required. The other is uncached and cached. So when I say it's uncached, means the page is needed by a process, but it's currently not cached in the DRAM. Okay, if it's cached, means you mark it as cached. That means you need it in the process and it's already cached. Okay, so the main difference is if it is already cached in the DRAM, that means I already have a working copy nearby. Okay, so I don't need to go out to get it. Okay, so that is really available for me to access. So that is the key thing of how or what you mean by the page is already cached. Okay, so as you can see here, this is basically what it looks like, where you have pages. All right, that means your entire virtual address space is broken up into blocks, okay, of a particular page size. Okay, and as and when, okay, you say that a particular page belongs to a process, I copy that data from the virtual address space over to the physical address space. Okay, and subsequently I access it from the physical address space. Okay, if it is not belonging to the process, then it's fine. Okay, now when you talk about virtual memory addressing, okay, you can map to, of course, the physical memory or the actual hard disk. All right. So when it's mapping to the hard disk, that means it is still not cached in the physical memory yet. All right. So that is something that we need to handle. All right. So let's look at an example here. So let's say I have 16 kilobytes of virtual address. So 16 kilobytes is basically to the power of 14. Okay. So you get 16 kilobytes. And 4 kilobytes is 2 to the power of 12. All right, and I have a page size of 64 bytes. Okay, so the first thing that you want to know is how many pages am I going to get? All right, so since I have 16 kilobyte of virtual address space, 16 kilobyte divided by 64, I'll have 256 virtual pages. Okay, for the physical, it will be 64 physical pages. Okay, so you can see what we're trying to do. We are having 256 virtual pages, and I'm trying to map it to 64 physical pages. So definitely I can't fit everything in. So I need to decide, okay, as and when who gets to occupy the physical space from the virtual space. Okay, so there's a question, why is DRAM used as cache for virtual memory? What about SRAM? So SRAM is used as the cache when you are doing the access of between the DRAM and SRAM. So it's two sort of levels of caching. Okay, so between DRAM and SRAM, there is another level of caching. Okay, so between DRAM and hard disk, that is another level of caching. So the caching between the DRAM and the hard disk is the whole idea of virtual memory, because your actual program is very, very big, which can't fit into the virtual memory. Okay, so you can only keep portions of the actual program in your DRAM. And from the DRAM, when you're accessing it, parts of it gets copied over to the SRAM. Okay, so in general, you have two levels, correct? But the concept is the same. Okay. Okay, so now that we know how much space, how many pages we have, okay, for the virtual and physical. So since for virtual pages, I have 256 pages. Okay, I need 8 bits. Okay, 2 to the power 8 will be 256. Similarly, I have 64 physical pages, so 2 to the power 6 will give me 64. Okay, that means I need 8 bits to access all the pages here. Okay, so in my virtual space, okay, I need 8 bits. Okay, so 0x1 2 3 4 6 7 8. Okay, I need 8 bits to access all the virtual memory locations. Okay, so for the physical memory, I need 6 bits. Okay, 1, 2. So I need a total of 6 bits to access all the physical memory pages. All right, but those are only the pages, correct? So within the pages, you also need to access the actual bytes within each page. Okay, so if you look back here, when I say I have one page, so in this case, I have total of 256 pages. That means this is page 0, okay, then page 1, and then page 255. Okay, comes here. But within each page, if I zoom in here, within each page is another 64 bytes of data, right? Because each page is 64 bytes. Okay, so within each page, I have 64 bytes, and I have a total of 256 virtual pages and 64 physical pages. So I need to do two levels of access. One is I need to access the correct page, and within the page, I need to access the correct byte. Okay, that I'm interested in. So that is why you need to break it up into two parts. So one is the page offset. So the page offset is fixed. Okay, in this case, since I have 64 pages, okay, I need 6 bits. Okay, that is fixed for both the virtual and physical. Okay, and for the virtual, I have a total of 256 pages. Okay, so for 256 pages, I need a total of 8 bits. So that is why you have 6 to 13. Okay, similarly for the physical page, I have a total of 64 pages. Okay, so that is why you have 6 bits. All right, so that is how you sort of come up with the address or the number of bits for the virtual address and the physical address. Okay, so now how do we do this translation? All right, so what I need to have is I need to have a page table. Okay, so a page table needs to provide me with this information where I am able to translate my or map my virtual pages to physical pages. Okay, so if I look over here, what you can see is I have a page table entry, okay, where 1 bit is indicating that it is valid. Okay, so what is valid? That means it is cached. Okay, so when valid is 1 means I have cached the data from the virtual memory to the physical memory. So you can see that, for example, page 1 and 2, okay, 4 and 7, they are all cached. So I have a copy of them inside my physical memory. Okay, whereas the other 2 over here are uncached. Okay, and 1 is not allocated. Yeah, so 2 is not allocated. So 2 is uncached. So you can see that what happens. Okay, if okay, so we'll come to that in another slide. Okay, what happens when I don't get it? Okay, but basically what you can see is 1 page table per process. So when you create a new process, you automatically need to allocate a page table for that. All right, and that page table is also stored inside the main memory. All right, so in this case, I need to have the page table, and the number of page table entries corresponds to the number of virtual pages that I have. Okay, so as you can see here, depending on how many virtual pages I have for that particular process, I need that same number of rows inside this page table. Okay, because each virtual address space needs to be mapped, okay, to some physical memory. Okay, then like 0 means is uncached and 1 means is cached. So this is an example of a page table, all right, where you can have a physical page number and the actual valid bit. Okay, so as you can see, if it is having a value, then it is cached. Okay, so the valid bit is 1. If there is no value, that means it is still on the hard disk, so it is uncached. Okay. Now coming back to this example here, let's look at how big your page table has to be. All right. So as we saw just now, I need 1 page table entry, okay, for 1 virtual page. Okay. So since I have 256 virtual pages, I need 256 page table entries. So inside this page table entry, what do I need to? What is the information I need to hold? I need to hold the actual physical address that I'm going to map to. Okay. So since in this example, I need 6 bits for the physical address, physical page address. I need 6 bits for that. Plus, I need 1 more bit to indicate whether it's valid or not. All right, so I need a total of 256 multiplied by 7 bits, okay, which is 224 bytes for this page table that I'm going to create for this process. Okay, so this example, this slide here shows you what happens, okay, when you're trying to access a particular memory location. Okay, so this is the address that the processor sees or the processor sends out. Okay, and then what happens? Once the processor sends out this address, okay, then this is the address I'm interested in accessing. That address gets split into 2. Okay, the page offset is the same for the virtual and physical, so that one I can immediately take a copy of it. The virtual page number points to what? Points to an entry inside the page table. Okay, so as we saw just now, there are as many page table entries as there are virtual addresses. All right, so in this case, I mean, as there are virtual pages. So in this case, if I have 256 virtual pages, each page number will point to a particular virtual page. So when your virtual page number points to a particular page, let's say in this example here, what do we do next? We will check whether the valid bit is set or not. Okay, if the valid bit is set, then this contains a correct physical page number. I take the physical page number and copy it over here. So now, once that is done, I have translated my virtual address into the actual physical address that I can now go and access. All right, but what if this was not valid? Right, the valid bit is 0, then it leads to a page fault. Okay, which we then need to handle after that. Okay, so let's look at what happens when it's a page hit. So when it's a page hit, okay, you access a particular entry in the page table, okay, and the valid bit is set, means this is the data that I want. Okay, so I can directly take it and use it. But if it is not there, okay, then that is what we call a page fault. Okay, so in this example, I'm trying to access this, but my valid bit is 0. Okay, so in this case, it is used by the process, but it is still uncached. It's pointing to the actual disk, not the DRAM. Okay, so what I need to do, I need to do a handling of a page fault. Okay, so when I do a handling of a page fault, what happens is the OS must load the page from the disk to the physical memory. Okay, and once it loads it to the physical memory, it must also update the page table entry. Okay, to correspond to the virtual page, and then it has to rerun the instruction again. So there's a second attempt. So there'll be 2 attempts. So the first attempt will fail. Okay, and once the OS realizes there is a failure because of a page fault, it then needs to do these steps. Okay, which is to take the actual memory, okay, from the disk and do a copy over, and at the same time update the page table entry, and then I rerun my instruction. So in this example, what will happen is, okay, I will need to do the same process. Okay, so in this case, I may choose to select one victim. Okay, when you say a victim, means basically one of the pages that is currently being occupied that has to be kicked out. Okay, so once one page is selected to be kicked out, then they will take the new page and occupy it. Okay, so previously this, so currently this is virtual page 4, and if I select this to be removed, then virtual page 4 will now come back to the, or will now have to still map to the disk, while virtual page 3 is now in the DRAM. Okay, so who gets to be evicted again is there are different policies. Okay, so we're not going to go into details. It's just like, for example, last week's studio on memory allocation, correct? So there's first fit, best fit, next fit, and so on. So there are different policies. So similarly, for this kind of caching and virtual memory, there are also policies on how to select which page to be evicted. Okay, so in some cases could be the one that has been there for the longest time, or the one that is not being used for a certain amount of time, or so on. Okay, so there are different policies to some algorithms to decide which page will get evicted. Okay, and then a new page will take over that. Okay, but we're not going to go into those details here. Okay, so once you have already updated the virtual memory and the page table entry, okay, you can see that now the valid bit is updated to 1, which means that when I restart the instruction, I'll get a page hit. Okay, so that is basically how the whole concept of virtual memory works. Okay, and as we said in the beginning, that it works well because of locality. Okay, the idea of spatial and temporal locality. Okay, where you have a set of virtual pages where you actively access it, okay, during that period of time, before you move on to some other working set. All right. So if the working set size is smaller than the main memory size, then of course it works. But if the working set size is greater than main memory size, then is what we call a thrashing happens. Okay, so what do you mean by this? So for example, here I have 4 blocks of page set. Okay, so my DRAM can hold 4 blocks of 4 pages. All right, and let's assume that you at any point of time you only need to use one of those blocks, okay, or 2 of those blocks. So when you're running the code, you don't need to every time change. But let's assume that your process requires or the memory, the way you access the memory is across many pages, such that you always need to keep thrashing the memory. Okay, so for example, if I create an array, okay, like I said, so if I say this is my first element I access, then I go to x1 and I access and so on. So that gives me that spatial locality. All right. Okay, because in general you may access variables nearby each other. Okay, so when I access x0, okay, then what happens? Okay, this entire page. Okay, let's assume this is the page size. So this entire page will go into one of the actual DRAM pages. All right, and then I can access this one and all the subsequent ones without any issue. All right, but let's assume that the way you have written the code or way you access the memory is such that the first one I access here, then the next one is in another page. Okay, so I say xn, and this is another page, and so on. All right, and then again the next access is xm, which is also in another page. All right, and you do a sequence like that: x0, xn, xm. So the way you or the way the program is accessing variables is such that it's always in some new page. All right, so that is where you may be forcing the system to keep on swapping pages. Okay, if you run out of the actual DRAM space already. Correct. So that is what we call the thrashing. Okay, that means your program is written such that the access is always across different pages. Okay. Again, this is usually not the case. All right, because in most cases we do. I mean, the way we write program, the way we data is stored for most, let's say images or audio clips or video clips, is always next to each other. Right. So again, this is a case where maybe exceptional. All right, where in some case where the data is really sort of spread out. Again, you do have to access it in that particular sequence. All right. So of course, these kind of things will have a huge impact on the performance. All right, and sometimes you may need to rethink the algorithm. All right, instead of trying to do memory access in this way, can you still do it linearly and then change the way you process the information? Okay, so that you don't have to thrash your memory system like this. All right, so the whole idea is this virtual memory again works across multiple processors because you just copy the whole thing again and again. Right? So every time you launch a new process, it has its own virtual address space, which maps to its own physical addresses. Okay, so of course that leads to the issue of two virtual memories maybe trying to access a common page. Okay, in the physical memory. Okay, so again, this might come across. So how do we deal with it? Okay, so one of the advantages of virtual memory is it does not require contiguous allocation in the physical memory. All right, so even though inside the virtual space, your code may be all written in sequence, correct? But when it gets allocated to the physical space, it can all get sort of mixed up, and it doesn't matter because the address translation is still going on correctly. Okay, so it doesn't have to be in a contiguous allocation of memory. Okay, so there is no external fragmentation. Okay, so of course there may be some internal fragmentation if your process uses only part of the page allocation and some part of the page is not used. Okay, but again, that is again part of how it works. Okay, so in terms of protection and sharing, all right, so one thing is, in this case, for example, you have a page 6 that is shared. All right, so when it's sharing, okay, what can you do? Okay, so that's one thing. The other thing is, you also have a built-in protection mechanism because a process cannot access a physical page if it does not have a mapping for it. So as you can see, for example, process 2 cannot access physical page 2. Physical page 2 can only be accessed by process 1. Okay, so there is an inherent protection, okay, where a process can only get access to the physical spaces that it has a mapping to. All right, so that protection is good. In terms of the sharing, okay, and protection as well, one of the things that is built into the MMU is what we call this permission bits. All right, so in a processor, okay, the MMU has some sort of protection bits where you can say whether you allow write access, whether you allow execution of code in that particular memory space, and so on. Okay, so you can sort of have certain permissions to protect certain regions, okay, of your physical address. Okay, so that gives you again a kind of a protection. Okay, and if your code tries to do something that is not allowed and the MMU detects it, it will usually flag out as a segmentation fault. Okay, that means you have tried to do something to a memory region that is not allowed. Okay, so that is what usually comes out as a segmentation fault in the system. Okay, so this is again just to summarize the whole thing of what is a address translation hit. Okay, so in a address translation hit, you send out the virtual address. The MMU looks at the page table entry, okay, in the memory. Okay, so this page table is stored in the memory. Okay, so it needs to access the memory, okay, to see what is the actual page table entry, okay, based on the virtual address given. Okay, and once you get the page table entry back here, then you are able to send the correct physical address out, okay, to the memory and get the information in. If there's a page fault, okay, if there's a page fault, then what happens? Then you need to do these two things, all right? It means you need to get rid of one of the pages currently. Okay, you evict one of the page and you take the new page in. Okay, and of course this is managed by the exception. Okay, so a page fault exception will automatically be triggered, okay, by the MMU, and all of this will happen in the background. Okay, now when you look at this process, one of the things you realize is that the page table entry is also stored inside the DRAM. Okay, that means I actually need to access it twice, right? Because I need to first access it for the page table entry, and once I get the page table entry that maps the virtual memory to the physical memory, I need to access it one more time for the actual information that I want. Okay, so this sort of counterintuitive, because the whole idea is you want to minimize this slow memory access. So one of the ways we can sort of minimize it is we can actually do some another layer of caching. Okay, another layer of caching to make it faster. Okay, so what we can do is we can actually put aside what we call a translation look aside buffer, okay, inside the MMU itself, okay, which is actually a small subset of the actual page table. Okay, so what you can see is you have the full page table inside the DRAM. But instead of keeping the full page table or instead of trying to access it through the DRAM all the time, within the processor itself, I have a on-chip TLB. So it's the same as how we look at the onboard cache, the SRAM. Right, so the processor has an onboard SRAM to cache from the DRAM. Now, for the page translation itself, you have a on-chip translation buffer to hold a subset of this translation of stable entry. Okay, so what will happen is when you put out a virtual address, instead of going straight out to the memory, it looks inside here first. Again, it's very fast because it's within the chip itself. Okay, and this TLB is actually a subset of your actual page table entry. Okay, so I take a subset of the page table entry and put it inside here, and then I go ahead to access. Okay, but again, as before, it is only a subset. So after a while, you probably have a miss. Okay, so when there's a miss, then you need to go to the page fault again. Okay, so this gives you the overview again. So as you can see, your virtual page number points to one line inside your page table. Okay, and once that one line is there and if the valid bit is set, then you take a copy of your physical page number, your page offset, and you get the actual address that you want to access. So this is the physical address. Okay, so if it's a hit, no problem. All right, that means you can directly put everything together and direct access the information from the memory. Okay, if it's a miss, okay, what happens is, of course, you need to do a few more steps, correct? Because then you need to update the TLB with the actual information from the page table entry, and then you pick the data and update. Okay, so it is again another round of updating the TLB. Okay, but again, why it happens only once a while is because of that, again, concept of locality. All right, so that concept of locality helps us to use all these on-chip TLBs and cache and so on to make our system much faster, right, and minimize the access to the external memory as much as we can. Okay, so again, this sort of puts everything together in terms of what's happening. All right, so you have a virtual address. Okay, go to the MMU. Okay, if it's a hit, good. If it is a miss, okay, again, your page table. Okay, then you need to come back in to update. Okay, when you update it, then you restart it, then you get a page hit, then you access it. All right, if the page table, that means the buffer inside also has a miss, then you also need to take the page fault and do another page table update. All right, so this sort of gives you the overview of everything that is happening, all right, and how it works. Okay, so the whole idea again between virtual memory and cache is a system that allows us to speed up the whole process of executing our code, all right, because memory access is very slow. Okay, and the general idea is we try to keep as much information as possible closer to the processor and make it easier for it to access this information regularly. Okay, and as and when we need, then we swap out with new data, okay, when we need it. Okay, so this last few slides is just on the DMA concept. Okay, so the DMA is just another peripheral, okay, to provide a means of transferring data between your CPU and your peripheral without direct intervention of the CPU. Okay, so why it is very useful is because you can do movement of data between one memory location and another memory location without actually using the CPU or executing instructions. Okay, so your data throughput is very high. Okay, so a DMA generally looks like this, where you have a DMA controller, and inside the DMA controller, what you can do is you can configure it to move data around from one location to another location. Now, of course, when it moves data around, it needs to take over the address bus and data bus. So that is where you have the bus switch. Okay, over here and over here. So you can see that when the CPU is using the executing instructions, you will take or make use of the address and data bus. When the DMA is taking over, it will take over the address and data bus. Okay, and once it takes over, it can do data transfer, okay, between one address and another address. Okay, and usually it can happen through two ways. One is your peripheral might initiate data transfer, okay, or you can initiate data transfer. Okay, so for example, when you, let's say you drag a movie, a very big file, let's say a movie, okay, from your hard disk to your thumb drive. Okay, so you're initiating a data transfer which is very big. Okay, and what your USB subsystem might do is it might initiate a request to the DMA controller. okay, to say that it needs to move a large amount of data from one address to another address. And once your CPU grants the DMA cycle, your DMA will approve it, okay, and the transfer will take place. Okay, so of course, once the transfer is taking place, your CPU is also sort of freed up, okay, because the DMA is now able to make full use of the buses. Okay, so again, the processor also can initiate it, or the peripheral can initiate it. That means you yourself, in your code, you can write a code. You can write some software to say that I want to move a certain amount of data from one location to another location. Okay, and then you say I want to initiate the DMA to do this move. Okay, so most DMAX, okay, have different channels. If you look back at our KL25Z, I believe we have about 4 or 6 channels, I think, okay, of DMA. All right, which means you can actually do a lot of data transfer concurrently, okay, using the DMA blocks. All right, now when you talk about DMA, okay, generally we say the CPU is halted. All right, and that is in what we call the burst mode of operation. Okay, so you can operate the DMA in 2 modes. Okay, in the burst mode, what happens is, once I say, for example, here, once I say I grab the data transfer, then the peripheral takes over, the peripheral and the DMA sort of take over the entire bus, the address bus and data bus, and complete the data transfer and then give control back to the CPU. Okay, the other alternative is what we call the cycle steal mode, where your DMA and CPU can interleave. All right, so in one half of the clock cycle, your DMA can use the bus, the other half, your CPU can use the bus. All right, and this allows both of them to like interleave and share the time. And again, why it is still better is because during this time, your CPU can still do something meaningful. All right, while the other half of the clock cycle, your DMA can do something, can carry on with the data move. Okay, so again, that is just a quick summary of the DMA, okay, just to give you an idea of how DMA works. Okay, so even though we did not try it out, okay, it is available on the KL25Z, so you can always try it out when you're free. Okay, so in terms of virtual memory, I think we have covered the concept, okay, how it works and why it is needed, okay, in a system. And DMA sort of gives you the advantage of moving data around very quickly. Okay, so with that, we have concluded the module. Okay, so congratulations. Okay, yeah, so a few things. Okay, so let me move on to the admin matters first. All right, of what we need to do. Okay, so this module, like I said, has always been a work in progress. Okay, and we are continuously trying to see what we can do to make it better. Okay, so if you have feedback or other things that you want to discuss, you can always let me know. All right, and then I will look into what we can do for the next batch and so on. Okay, so let me go to some admin matters first before we go for a break. Okay, so the submission folders for the project deliverables will be open in Luminous. Okay, so the deadline for all submission is next week, next Friday. Okay, so that is the deadline for you to submit everything that is due. Okay, so I will send an announcement on this again later. All right, so you have after this Friday's completion, you have 1 more week to finish out everything. Okay, so of course, don't wait until the last minute. If you are done, okay, and you want to submit earlier, just go ahead and do it. Okay, then you can focus on other things. Okay, for the TA application, again, if you are interested, please apply to the SOC portal, all right, and complete the online course. Okay, you need to make sure you indicate the modules you are applying for, all right, then only the module coordinator will get the information. Okay, if you just apply but you don't indicate the module, then you won't get that info. All right, I also open up a poll in the Luminous so that I know who is applying. All right, as I said before, okay, placement cannot be guaranteed, okay, because there's only a limited number of slots available. Okay, so just look out for all the modules that you're interested in. Okay, generally we also need TAs for the EPP2. Okay, so if you're interested in that, also please apply. Okay, so the EPP2 has changed name in case you did not know. Okay, it's now called CG2111A. Okay, so EPP2 has now changed name to this. Okay, so please apply for that as well if you think you are interested to be a TA for that. Okay. Okay, so the exam. So this one I'll go through again later, but let me just brief you off first. Okay, so I have sent an announcement, okay, on the exam details. All right. So the first thing is it is a closed book with the provided reference sheet. Okay, so the provided reference sheet is this document that I've uploaded. Maybe I should open up the document. Just give me a minute here. Let me open up that document so you can see. Okay, so this is the exam reference sheet that I've already uploaded. Okay, so this is the exam reference sheet you can use. Okay, so you're not allowed to create your own one or bring anything else. Okay, so as you can see here, basically I've just given you all the OS related APIs, okay, that you may want to refer to. Okay, and the priority mapping here. Okay, so that is basically the only reference sheet you are allowed to use for the final exam. Okay. Yeah. Okay. So, and you're only allowed to have a soft copy of this reference sheet. Okay. During the exam. Okay. So please have your calculator also on standby. Okay. The Zoom proctoring and screen recording are all as per normal. Okay. That you should know. Okay. In terms of topics covered, it will be from lecture 9 onwards. Okay. Let me intro to RTOS onwards. Okay. The earlier topics, okay, will not be tested, okay, in terms of the low level configuration, okay, but the concept you still need to be clear. Okay, so what do I mean by concept? That means if the question says that you're creating a task and then the interrupt is sending a semaphore or something like that, so you should know what a semaphore, what an interrupt is, correct? Okay, or some data is coming in through the UART terminal and you're using a message queue to capture it or something. Okay, so the UART you should know. Okay, so the general idea of those peripherals you should know, all right? But how it's configured, how to generate a particular baud rate or PWM, those kind of things I will not ask. All right, all those already covered in the midterm. Okay, so it's just a general concept of those peripherals you should know. Okay, but no details are required. In terms of the format, you have MCQ and true false, okay, which will be about maybe 20-25%, and the rest will be structured. So when you say structured questions, there will be some questions where you may need to write some code. Okay, so of course, when writing code, I will specify clearly what you need to write, what you don't need to write, and so on. Okay, so for example, if you are required to write a task that is going to do something, okay, I will clearly say that, okay, maybe you don't need to write the main function where you create the task. Okay, that one is considered already given. So you just write the actual task that you're supposed to do, yeah, something like that. So I will specify what you need to sort of provide in the exam. So I'll also be creating sort of a sample luminous quiz exam just to give you an idea of how to use the answer box. All right, so in the luminous quiz, the answer box, you just need to be familiar with sort of writing code inside, okay, and then answering it. Okay, so if you look at past year papers, again, some coverage, some topics will be different. Okay, so if you don't see anything familiar or you see something that you're not familiar with, okay, it's not covered in the class, then it's not part of the current syllabus. Okay. Okay, so that's all I wanted to say about the exam. Okay, maybe we'll go for a break first. Okay, then we'll come back and then I will answer any questions you have on the exam. Okay, and then we will go through the tutorial. Okay, so we'll go for a 10 minutes break. Okay, and then we'll come back and then I will answer any questions you have. Okay, so I will come back to the exam again later on. Okay, let's go through the tutorial 8. Okay, so this tutorial basically questions from this last two lectures on memory and today's on virtual memory as well. All right. So the first question is on this, where you have holes available in the memory, okay, with these particular sizes, okay, and you have 3 processors that require an allocation of 12, 10, and 9. Okay, and how would memory be allocated? Okay, based on these 4 policies over here. Right, so if you look at it, okay, so what does first fit do? So in first fit, you will always go to the beginning, okay, of the space available, and from there try to see the first hole that is able to satisfy the requirement. All right, so when I want to take allocate 12 kilobyte, I will look at the first hole. First hole is only 10, so it's not available. Second hole is 4, not available, and the third hole is 20. All right, so when the third hole is 20, I will immediately allocate 12 out of the 20, and I will sort of complete that allocation. Okay, when I want to allocate for the 10 kilobyte, again I go back to the beginning, and since the very first hole is already 10 kilobyte, I'm able to allocate. Okay, and then subsequently when it comes to 9, okay, the first hole available is here, and again 4 is too small, then the next hole is here, 8 will be too small, and then the third hole here is 18. So out of 18, I can allocate 9. All right, and then the 9 is free. Okay, so that is how you get this allocation for first fit policy. For best fit, okay, what you do is you will traverse through to see the closest matching size based on the requirement. So when it wants 12 kilobyte, I will traverse through the entire space to see what is the closest to 12. And since I have a 12 kilobyte space, that will allocate to this request. Similarly, 10 will go to the 10 kilobyte request. Okay. And finally, the 9. There's also a 9 kilobyte hole, so that gets allocated here. All right, so the best fit will use the best size hole possible to fit the required size. Now, what about worst fit? So in worst fit, the policy is to use the biggest hole possible to fit the required size. Okay, so when I want to fill up 12 kilobyte, I will go through all the holes and find that the 20 is the biggest. Okay, so since 20 is the biggest, I'll allocate 12 to that. All right, when I want to do 10, again, I go through all the holes, and the biggest size at that time will be 18. So I'll allocate 10 out of the 18. And finally, when I want 9, I'll again go through all the holes, and the biggest hole is 15. So out of 15, I'll allocate 9. Okay, so that is the worst fit policy. Okay, so in next fit, basically what happens is you look for the first available hole that can fit the required size, and then you carry on from there. Okay, so when I want 12, okay, when I traverse through the holes, I will see that the first hole is 20. So I can fill it up with the allocation of 12. Then the next request of 10, I carry on from there. So since I already fill up 12, my new, the next hole is pointing here. Okay, and this hole size is 8, not big enough. Then the next one is 18. So out of 18, I can allocate 10. Okay, so next my pointer is over here. And then the last one is 9. So again, 8 is too small, 7 is too small, and then I had 9. Okay, then I allocate 9 out of the 9. Okay, so that is basically the way in which memory allocation will be done using these 4 policies. Okay, this question 2 is basically on the concept of what goes where, right? In terms of the data, the variables, the code, and so on. Okay, so generally we can say that the entire code space goes into the text segment. Okay, so that is the whole code that you're going to be writing for the main and the sub. In terms of the allocation of the variables, F and Y are both variables, global variables with initialization. Okay, so once they initialize to a value, you will put them in the data segment. Okay, X and asterisk P, pointer P, they are both global variables, but they are uninitialized, so they will go into the BSS segment. Okay, there is a malloc here. Okay, so this malloc will be allocated on the heap. Okay, and finally the stack is for the variables that are considered automatic. That means as and when the function is invoked. So for the main, you have G is automatic variable, and then you create 2 more spaces for the parameters that you're going to pass in when you call sub. And finally, inside sub, you create another automatic variable C. So A, B, and C are on the stack. Okay, so that means once you come out of the sub variable, they are not accessible anymore. Correct. I mean, they're still accessible to a stack pointer, but we consider that we already cleared from the stack. Okay, so I mean, if you recall from your assembly language concept, okay, your stack pointer, the way your stack works is basically you have a stack pointer that points to an address, correct? So when I say I pop some data, correct? So I say I pop A, B, C, and then your stack pointer is pointing here. Okay, or maybe here. Okay, so again, depends on how the stack pointer is designed. All right, whether it's pointing to the last allocated space or the first free space. Okay, so whatever the case, let's assume that right now I come out of the stack. That means I come out of the function sub. So after I come out of the function sub, my stack pointer is pointing here. Okay, it's pointing to G in the main function. All right, now it doesn't mean that ABC has been cleared or reset to 0. Right, it is still there in the memory. Okay, but it's just that we sort of consider pop it from the stack. Okay, but it is actually still retained there in the memory. If you manually try to access it using a pointer or using the current stack pointer plus an offset and so on, you are still able to retrieve the values. All right, but that is just like a hack. Okay, because you should not think of using the stack that way. Okay, as and when you need to push or you pop, then you use it just based on the current stack pointer value. Okay, but technically, if there is no other override to these values, then these values would be retained there. Okay, that means if I don't call another function or there is no use of the stack after that, okay, then they are still there until the system sort of shuts down. Okay, so for virtual memory, okay, again, we just covered it, all right, but this question is just, I think, fairly straightforward. Okay, where you have 64 bytes per page. Okay, and you are having a system where you have 10-bit virtual address and 9-bit physical address. Okay, so the number of bytes of virtual memory again depends on the number of bits you use to allocate them. So if I have 10 bits, so 2 to the power of 10 is 1024 bytes of virtual memory, and 9 bits physical address means 2 to the power of 9 is 512 bytes of physical memory. Okay, so they ask what is the maximum number of virtual and physical pages. Okay, so the number of pages is basically the size divided by the page size, the total number of memory size divided by the actual physical page size. So in this case, we are having 64 bytes per page. All right, so which means that if I take the total number of size over here, 1024 divided by 64, I will get 16 virtual pages. Okay, similarly for physical, you have 8. Okay, another way to look at it is just look at it from the number of bits. Okay, so since I know that I have 64 bytes per page, 64 bytes translates to 6 bits. Okay, so 6 bits is set aside So this 6 bits over here, as you can see, is set aside for the byte index. Okay, that is to access the bytes within each page. All right. And since I have total of 10 bytes for the virtual page, I have 4 bits left, and 9 bytes for the physical page, I have 3 bits left. So that gives us an indication of how many virtual pages there are and how many physical pages there are. Okay. Okay, so this last one is this part here is to just get a review of how we do the translation. Okay, so if my virtual address is 0, what does it translate to? So here we have already given you the page table entries. All right, so what we need to do is the process is quite standard. We first again split up the addresses based on the page size. Okay, so since my page size is 64, I need 6 bits. So the lower 6 bits are common. Okay, then the upper bits refer to the actual page number of the virtual mapping. So for the virtual address, the upper 4 bits 0000 point to table entry 0. Okay, so since table entry 0 is a valid one, that means it's a valid page table entry. So the page number there is 2. So I take a value of 2 and put here. So this combined value or address is now 128. Okay, that means my virtual address 0 maps to physical address 128. Okay, based on the page table entry right now. Okay, and then you do the same thing for each address. So if my virtual address is 15, okay, then I do the same thing. Okay, so 15 translates to 0000001111. Correct, but the lower 6 bits, as we know, is already reserved for the page offset. Okay, so what we now need to do is we take the upper bits. So in this case, the upper bits is 0000, which translates to again the same thing, page entry 0. Okay, and page entry 0 translates to a page number 2, physical page number 2. So the 2 comes here. So the total or actual physical address maps to physical address 143. Okay, so that is how you translate the virtual to the physical using the page table entry. Okay, so there's one more here, 576. So 576, again, if you convert to binary, you get this value. So you can see that the upper 4 bits is 1001, which is a value of 9. So that translates to table entry 9. So in table entry 9, the physical page number is 6. Okay, so the value of 6 will come here, and then the rest is copied from the virtual address, and that gives me a physical address of 384. All right, so you can see that you just need to repeat that process. Okay, and if you work through the rest, this is what you will get as the final answer. Okay, of the mapping between the virtual address and the physical address. All right, so that is basically how the mapping is done using the page table. All right, and this last question here is on the DMA. All right, so this question is just to reinforce the idea of why you want a DMA. Okay, so let's say you're creating a program, correct, where I want to move a large amount of data. So 1 megabyte of data is a lot, and I want to move it from one address location to another address location. Okay, and at the same time, okay, I want to update the data transfer every time I complete 1 kilobyte. Okay, by updating some LCD panel. Okay, so what are the ways in which I can do this? Right. So of course, the primitive approach would be to use. This is a small I. Okay, one of the primitive approach would be to just use a loop. Right, where I take the data from the source, copy it to the destination. Okay, and every time I fulfill 1 kilobyte, I update the LCD screen. All right, so that is something that will work. All right, but again, why this is very inefficient is because this whole memory move is not a real value add. Right, it's just moving data from one point to another point without any processing. Okay, so since there is no data processing involved, you just move. executing instructions to do this is a waste. All right, so that is where the DMA block comes in. So what I can do is, for the DMA block, I can configure the registers. So the DMA registers, okay, there are a few registers. Okay, so one is the source register that tells you where is the source data. The other would be the destination, okay, where I want to write to, and then the other one is the size, okay, or the count, okay, how many bytes of data I want to transfer. All right, so what I can do is I can program my DMA, okay, to keep transferring 1 kilobyte of data at a time. Okay, and as what we have seen, almost all peripherals have some interrupt capability. Okay, so you can configure the DMA to generate an interrupt every 1 kilobyte. So inside the interrupt service routine, then I can maybe update the LCD, and then I initiate. So when I say initiate means, what must I do? I must do this again. I must update my DMA registers again for the new source, new destination, and the size information. Okay, and I'll keep repeating this until I finish the entire 1 megabyte of transfer. Okay, again, why this is better? Because you only need to sort of program this in the interrupt. Okay, the very first time is before the interrupt. Subsequently, is only whenever the interrupt is triggered. Okay, so in between, while this data transfer is going on, you can still do things or do more meaningful things using your processing power. Okay, so that is the advantage of having a DMA or using the DMA system. Okay, so that's sort of summarized here. Okay, so again, that's all for tutorial 8. Again, just some simple questions to reinforce those concepts that we discussed today. Okay, so let me just flash back the slide on the exam. Okay, to take any questions if anybody has. Anything anybody wants to ask? Okay, so as I said, I will be creating a sort of sample, just 2 or 3 questions, sample quiz, exam quiz inside the Luminous, so you can try out, just to try out the answer box. Okay, how it will be when you start to retype code inside it and so on. Okay, so I have nothing else for today. Okay, so I will see you all in the lab on Friday for the final assessment. Okay, so just make sure you again, you have 40 minutes of lab time to work on your robot before the final competition starts. Okay, so I'll see you all on Friday. So thank you very much.